My name is Michał Nowak, and I am Technical Director at Techland. The last project that I made was Dying Light. My today's talk is about programming, so I will share my programming experience. I've been working as a game programmer for 13 years. The last 10 years at Techland, I worked on most aspects of game development. I've implemented player code in Call of Juarez, in SQL, Bound in Blood. I work on most aspects of game development. I write a lot of game and engine systems like save or animations. I could say that I'm a generalist who is not afraid to do anything. I've always been interested in improving what has been done. I love optimizing the budgets, the hardest problem, and fighting with TCRs. One of the biggest and hardest thing I've done is the multiplayer system in our engine using Dying Light. I was responsible for the design and the implementation of the whole network system. I didn't do it everything myself. I led the team who created the network system, but I wrote a lot of code line myself. Because I like to have a broad overview of what I do, we also added network functionality to multiple game systems. Now I'm technical director, but I'm still heavily involved in creation and maintenance of the network code. I could say that I'm an expert at this field at Techland. Today, I want to tell you about the whole network system. I always like to look from a distance at the issue that I'm responsible for. I want to have a broad overview of whole situation. So the network system is not only about transferring data, but also about how we use it, how we interpret data, how we should write code of classes, how we should make whole multiplayer game. So at the beginning, I need to explain what the game we wanted to make. It's very important to know that before we start writing any system. I will speak only about the key assumptions important from a network point of view. The next part I will tell you how the network system works. I will not speak about the details, I will not show you the code, I will focus on the most important things and concepts. Afterwards, I'm going to tell you about a few examples of gameplay problems that we came across and how we solved them. So what kind of game did we want to make? Dying Light is a game set in a big open world. The player is not closed in locked area. The player can free roam all over the world. Parkour and natural movement expands the freedom of movement even further, adds another dimension to the exploration of the world. The player can immerse themselves in the game world. There is a lot of physics simulated and destructible objects. The player can interact with objects and can change the world. There's a lot of zombies whom the player can fight or avoid them. The player can tackle quests in an order. And it's a co-op game with 4 players. And players can perform the same quest together, but they can also do completely different things. They can split all over the map and do separate tasks. Each of them can interact with physics world with no latency. When they touch, push, or use objects. And it's co-op game with 4 players. Players can join and leave at any time, even in the middle of quest. In co-op, player can do exactly the same things as they could do playing the single-player game. The multiplayer mode cannot enforce any additional restriction to the game. The game has to be as cool as in single player, or even 4 times cooler. We base our network solution on 2 key assumptions. First of all, we decided to make a peer-to-peer game. In open world games, there's a lot of objects, and you can't simulate them all on one machine. If you have 4 players running around the world, the server has to do the work for all players. If we use the integrated client-server model, the cost of simulation on a single machine becomes 4 times bigger. We couldn't afford it. We decided to simulate only the important objects around the local player. Each peer simulates its own objects and share the results with others. So there is no server which decides what the player can do. The game world is a combination of simulated objects from different peers. Each player is responsible for his or her own part of the world. Thus, he or she can interact with objects immediately, with no latency, if there is a 1 second lag. The only problem is that there is no one who decides how the world really works. The data don't flow in one direction, from server to client. For any object, any peer can be a server, so we had to solve the problem of who is responsible for the state of the objects. The second key assumption is that we synchronize the logical state of game object. We don't synchronize visual aspect of game object, we send the complete logical state of object. The state describes not only the current state of the object, but also all necessary information needed to simulate it. Each client simulates the object based on the same parameters. On all machines, the simulation to produce similar results, so we don't need to send the object data at every step of simulation. From time to time, we need to send a correction to make sure that the object looks the same on all machines. And if each player has a complete logical state of common objects, at every moment, the client can become the server for a single object, because it has all important data to become the object's owner. I was wondering how to explain how the network system works. Coding and testing network is a difficult problem to deal with. To explain it, I decided to use the tool that allowed us to make the network system. We made our own simple game. It has everything that Dying has. The big open world and a lot of objects. The objects are physics simulated, so we can push them. You can imagine that there are zombies we are fighting with. There are four players. All these players run in separate processes, and to synchronize data between them, we use the same network solution we use in Dying Light. Once more. As you can see, only the nearest objects are simulated. When we move around the world, if objects comes out of our interest range, they reset to its initial states. So we cannot change them. World has the same state all the time. We can forget about the rest. When we think our synchronization, we must focus on the colorful one. We can forget about the rest one because they are in the same state as they was after loading map. This gives us this simplifies our problem because we have to worry about the hundreds nearest object, not about thousands of objects from the map. It also fits with the idea of the game which we had. The player can travel the world back and forth. He or she often visits the same places. If the world resets, a trap can be reused when player returns. And there's a plague of zombie, and we cannot kill all zombies. Always somewhere, the new zombies comes out. Now let's connect. So now you can see that players share information about between each other. If players are far away from each other, they don't send any any data. If two players come close to each other, we must start to synchronize the data with them. And each player activates object only locally, and the network system knows that these are the same objects and connects them and share data between. We found there was one problem. If we only activate the object locally, if I, for example, push objects to another place, the other place don't know that that the objects are in their interest range. To fix this, so to fix it, each player sends its active range to other players, and now each player activates object only locally, but if some object is comes out its interest range and finds in other object interest range, we know that we should send the object to the other. All you need to do is focus on your active objects and check the ranges of other players for active objects. The network system will send the object for you. As you can see, the data flows only in one direction. So, red player is owner for its object. The green player is owner of his object. Red player can interact with objects, but sometimes or very often the green one don't have enough information to make the simulation good. So we had to find some way to switch object between peers. First of all, we decided that each player is owner of his character. So the red player owns the player character. If I own player character, I can move it with no latency. If I'm owner and authoritative for other for objects, I also can interact with them with no latency. But if I try to interact with other objects, something goes wrong. To fix this, we decide to allow change ownership at any time. So let's try. If player interacts with an object, he requests ownership, and immediately he becomes the object owner. So now the red one can interact with green objects with no latency. So these are the main concepts of our network. We can change ownership at any moment because we synchronize state between objects. We know the state of the object, and we can simulate. We can start simulation of object at any time. To write such code is pretty easy. let's imagine in our system, everybody simulates objects like it was single-player game. So on every peer, there is a simulation. One thing, we should identify a place where we should change ownership of object. And for doors, the state is open variable. If I want to change this variable, I do it only locally. So I need to find a way to its interaction. But if I change on remote peer, the state will be already. So I need to call single method, request ownership, and that's how we change our single player code into multiplayer code. We identify all places where the interaction is and call request ownership. We do this in collision handlers. We do this in all places where the interaction is. What I was talking about was simple. There's many other things that complicate the system. For example, what happens if two players want to change the same object at the same time? For an object, there will be two new states which are not always compatible with other. The network will decide which of these two states is the right one. It's always a win-lose game. So so if two players try to interact with an object, only one can change the object. It's always, there is no state merging, there's always win-lose game, and state from one object will be lost. But it's a role of the game to deal with that. If we interact, the network system can write our last things we do. How we do this? We do this in game. So I say you about another concept. We have state, which we share. We send between peer simulation, which runs on over all peers, and we have visualization. Visualization is what the player sees. It's another aspect of an object. It's not this. We don't see the state. We don't see is open, is closed variable. We see or model or animation. So because the state can change significantly from one frame to another after replication, we have to write visualization in a special way. We had to be sure that visualization can hide changes of state. I will try to explain on an example. Let's take a physics simulated object. To simulate an object, we need to synchronize its full state. We send the position and the velocity of object. Each peer simulates the object, but from times he receives different state, the correct one from the owner. Because physics simulation is not fully deterministic, it can be in different place. There can be an error. So we track the error, and we remember it. And after every render, and during every render, we add the error to its actual position, and it's what the visual position is. Of course, we reduce the local error each frame in a smooth way, and we do the same for orientation, the angular velocity. It's how we visualize all physics simulated objects. This technique is used for player object, for AIs, and others. I have mentioned that there are problems if two objects interact with if two players try to interact with one object. You know, the system works that if two players want to change the object in the same way, only one can do this. But this is a co-op game, and players have the same goal. So if two players want to use the same trap at the same time, it doesn't matter who does it. Everything works great when you can do only one thing with object, like with trap. So for this kind of object, we do nothing to fix the problem, fix the... Worst happen if we can do two or more things with an object, but we don't nothing there also, because good visualization helps the problem, and if they're grateful, if the more players are, if the more happens on the screen, the less attention we pay to all inconsequences. It's one situation where previous discussed solution is sufficient. It's fight with opponents. We can't allow that change from one of the players will be lost. Imagine the following situation. Two players beat a zombie. The first is cutting off the right arm and the second the left arm. Let's suppose that the left player wins. For him, nothing bad happens, but the other player receives the correct state, but with wrong arm cut off. It's not what the player expects. We cannot make good visualization where arms are growing back. So for fight, we have a different solution. Each player remembers and sends to others the last 10 hits. This is buffer with 10 last hits, and in each object, in each zombie, we remember the last few hits, and every synchronization we checked if all hits from all players were applied to object. If not, we apply them once more. So now both players see that both arms had been cut off. In our world is always resetting to its initial state. Sometimes it's not good. It's good if we are thinking about traps that we can reuse, so we can go back and refine them. It's not good, but if we have available loot at the chest, we cannot refill the chest after we leave the area and go back. It was so easy to abuse the system. So we remember locally, and the player remembers last 50 or more chests that he opened, and don't spawn any loot at them for half an hour. So if we can remember locally, we do this. We could do this the same way in single player game, but sometimes, for example, for a zombie, it's not good if we kill all zombies in a single area. For example, in a tunnel, players expect that there will be no zombie for some time. We cannot respawn them every time when player comes back. So we divide our world into areas, and if one player clears one area, sends information about this to other players, and how it's working. Don't do this for every single zombie, because we have a lot of zombies, but it will be a lot of data to synchronize. So we send only global information for areas, not for every object. And the last thing I want to say is how we how we find to change the world during the story, during the game. In our games, quests are used for telling the story, but also are the goals for the players, and quests describe the state of the world. So if we have, for example, quest built from multiple phases, if the spawn the zombie is the active phase, we know there is some special zombie spawn in the world. If kill the zombie is the active phase, we already know that the zombie was killed. If arm the explosive or explode the tower is the active phase, we know that the tower point in this quest was raised to the ground. Each whole state of the world is based on quest system, but we cannot run the quest system only on a single peer, because they can be on different parts of the world. So no one can know state of the whole world. If player is near the tower, or player is killing the zombie, and he must be responsible for the quest. So in our system, all players are responsible. All players are running quest system. All players knows the state of quest system is simulated. So if one player kills the zombie, he sends the quest state to others, and the others advance their quest state to most advanced state. Now, the red player wasn't near the zombie, but now he knows that the zombie was killed. We do the same for arm the explosive or explode the tower phase. Okay, this brings us to the final part. The whole network solution I've been talking about allowed us to make four multi-platform games. I think it's a good solution to our needs. If you want to make a co-op game or seamless developing game, I think it's a good option. But if you want to make a competitive game, I'm not sure this is the best option. Of course, we made the zombie mode in Dying Light or competitive mode in the Cartel, so we can try it too. But peer-to-peer has its limitation. There is no arbitration. There is no arbiter who would decide about the result or make sure that everything is fair. You need to connect all peers together, so you need to be aware of NIT limitation. And if you want to connect more players, the number of connection you need to establish grows squarely. Thank you. That's all. Sorry for my talk. I'm a little stressed, but maybe you have questions.
Would you share a little bit about the way everything is organized? I mean, you told about the architecture, but would you tell a little bit about the architecture of the system, like classes-wise?
Okay, we divide our system into parts. We have on the bottom, we have a lobby system responsible for connection with for matchmaking and connection with external matchmaking services like Steam or Xbox Live. On this, we built a connection layer. This connection layer use UDP to send data between pairs. The connection is responsible for connection between each peer. So the connection checks if we can establish connection with all peers, and on this we built network system. We call it replication layer because it shares data between them. This layer don't know nothing about game object. It knows only that there is some state and some of peer is some peer is owner of that object, and here is there is the part with changing ownership and making sure that only one owner is that there is only one owner at the time, and on this we build our game.
I was just wondering, do you also do like periodic integrity checks for the state, like run a checksum or something to make sure that the state is more or less coherent between the peers? Or does the system that you described already take care of that?
The system, the application layer takes care that on all peers the state is consistent, the same, and we worry only about the common object, shared object. So
you have described a system that seems to work well when players occupy separate space in your world. But isn't the usual case that people occupy the same space as they fight side by side?
yes, it's players often occupies the same space, but in the same space they have the number of objects in the same space always constant. Always there is around me. Always there is 50 zombies. Sometimes they are shared, but we can all peers simulates the zombies and move them from point to point, and from time to time the owner sends corrections. So visualization and similar result of simulation make sure that everything works. And if you interact with object, we immediately switch the ownership of the object, so we can become owner, we can simulate, we can be authoritative for the object. It's not very common that we we fight for ownership of many objects. We fight with one zombie, or together, or two players fight with two different zombies. So everybody has his own zombie.
But do you have any precautions about situations where you would have like two players trolling and just trying to open the same door from both sides, just repeatedly, so that you just have a ping pong of the ownership claiming? I mean, is there anything? Do you have any special solution for that, or does it just not occur often enough to be a problem at all?
I think it's not a big problem, but we have one solution for this. First of all, the solution with cutting hands is a way to merge states, allow two peers do different things with one object. Another solution which helps us is that in our game, all interaction take place. So if we want to open the door, we first play animation with hand and then open door. So during this time, the other player cannot change ownership for the object. So it's our solution.
How much traffic there is between peers, like on average? In bytes, yeah. Yeah, like I'm just curious. For a game like Dying Light.
If I want to be honest, I don't know. We don't check it last time. This the solution because we send state and between states we can do simulations. So we don't send state every frame. We skip frames. We check our solution on in previous game on. So it's adaptive. It can run on 100 kilobits per second, I think. But it would be the best gaming experience.
And how big is the area of influence around the player?
It depends. In the bigger object is the area is it's not the same for object. In bigger object is if we need we need simulate from great distance. So for AIs is I think between 50 or 100 meters. Rather 50. The rest of them are other system like crowd made by Janusz sitting there. So we only it's about 50 meters. Thank you.